So this problem is just following straight from where we left off. There is no new material with this. My big thing that I want to show you, I don't think I showed you the Npp plot last time. Is that correct? Didn't get to show you guys that. That's okay. I'm just going to show you why I like it. I actually think it's easier than a histogram. You'll see. Okay. So first off, let's go through all of the stuff that you needed to show for this. Preferably not too fuzzy. Okay, so the first thing that I did is I identified what we were talking about, and it was the average weight of the Lay's Ruffles, and I should have said that that was the bag that was marked as 28.3 grams. My pen's dying. Okay. Bless you. Now, when we go through our assumptions and conditions, first off, for independence, it was not randomly selected. Did you guys catch that? It did not say randomly selected. And when you guys do your end of the year projects, you're going to see that you're limited by what you can do. So you just grab bags off the shelf. That's the best that you can do. So we're going to say we hope it's representative. Good. And 6 is definitely going to be less than 10% of all bags. I mean, I hope Lay's makes more than 60 bags of potato chips. This is like a special edition, but even then, I digress. All right, this guy on the left, that's the Npp plot. That's why I like it. It is a plot of dots. That is it. How do I get the Npp plot? So I already had my data in list 1. The Npp plot is simply doing second y equals, and you're going to go to the, You're going to go all the way to the end over here. That very last one is the Npp plot. And it's going to pull your data from your list. The Npp plot, the reason I didn't do it the last time was because I was trying to be smart and funny and put all of my values in one list and frequency in list 2 to show you could do that. If you have that, you can't do an Npp plot. So you put it all in one list, you can do an Npp plot. And what that's doing is that's going to go through and calculate the z-score. And yeah, I said z-score. It's not that big of a deal. The z-score for every single one of the values, and it's going to plot them. So along one axis is the actual value itself, like how many grams it is. And on the other axis is a corresponding z-score. All you want, when you see this zoom stat, you want it to look like a line. That's it. That's why I like the Npp plot. It looks like a line. It looks like if I were to kind of go from corner to corner, it's not perfect, but from the top dot to the bottom dot, it's pretty much a straight line. You've got a little bit of a curve here, but that's literally what we say, straight enough. And now you know why I like Npp plots. A little bit easier. And when we to the histogram, the Npp plot is a lot easier to say straight enough than it is to say looking at the histogram when it's zoom stat, that's nearly normal. Do y'all understand what I'm talking about with that? You can also, I usually don't recommend it, but I've seen them do it on the AP exams. You can do a box and whisker plot, and you want it to look generally symmetric, and you don't want any outliers, but it's harder with the histogram, in my opinion, with the box and whisker, to make sure that it's not multimodal. You don't see that with this. You can tell that it's generally symmetric and that there are, but that's it. But any of those are appropriate. Heck, you want to do a stem and leaf plot? Do a stem and leaf plot. Okay, whatever works for you, but you're looking for that unimodal, symmetric, no outliers, or symmetric and no outliers. Everybody clear on that? Questions? Okay. So our conditions are in fact met. Did I get all my conditions? It feels light. We have independence. We have 10%. We no longer have a success failure. Now we have sample size with nearly normal. And that's a pretty small sample size. So we want pretty normal data. We're not going to get away with much here. Then part B said, find the mean and standard deviations of the weights. So this is just what my calculator popped out to me. And I honestly waited on writing that down until after I did the actual t interval, because that's when it gave it to me. I just kind of left it blank for that, and I came back and I filled it in once I finished the whole thing. Okay. And then it says, create the 95% confidence interval. So this is the sampling distribution. I really should have said what type of a confidence interval I'm doing here. What kind am I doing? A one sample t-int. You could have either put this formula with all the values in it, or just write the formula, but did you write t star? Everybody look at your paper. Did you write t star? That is a deal breaker if you don't do that. And then yay us, I get to be lazy and not do any actual math because shablam, it gives me the answer. I really love these calculators. They're just so nice. When I realized once I started teaching this, that I could have done this the whole time in college as my statistics class, I wanted to throat punch my statistics teacher. I felt it in my heart, but I wasn't going to actually do that. So, you guys look like today is your thriving day for energy and awakeness. You feeling like the weather today? Blah. Hey, it's Tuesday. It's not Monday. Yeah, there you go. This time next week, you won't be in school. You have Tuesday off next week. Primaries. Tuesday is primaries, and we are a polling place. So because we don't start off the school year with this planned. I don't know why. It should have been planned. But anyways, okay, coming back to this. He asked us to explain in context what the interval means. So I said, based on our sample, we're 95% confident. And I never write out the word confident because I don't spell good. The true average weight for bags marked with a net weight of 28.36 and 29.205 grams. You all right on our interpretations? Any questions so far? So, here? Oh, you mean Y, using Y or X? Nope. Nope. Just try to be consistent. So if you're using Y bar here, use Y bar here. Just be consistent. You know, there's really no big difference. Know why we use Y bar? Everywhere else I've been uses X bar, but our textbook says Y. I would be careful because, I mean, just picture the aisles at Wegmans or any of the other places. You go to the chip aisle, someone says, grab me a bag of Lay's, plain. You could go with the jumbo family bag, you can go with a standard bag, you can go with the individual size bags. So it's just being more specific as to what we're talking about. Now, would that be a deal breaker? I don't know. I've seen them work either way. Okay? Personally, if it was up to me, I probably wouldn't go crazy. But I've seen problems where they're like, nope! Big mistake. Okay? All right. And then it said, comment on the company stated net weight of 28.3 grams. What would you say? No. Okay, that's a word, not much of a comment, but somebody want to give me something? More than no? So your answer to that is no? Yes? I wrote, our sample provides evidence that the average weight of these bags is more than the advertised 28.3. I mean the textbook, talked about the idea of it's not in the interval. So more power to you. It's not in the interval. So there's evidence that it's more than. Okay? Not too horrible with that? We're okay? All right. So we've seen the only little thing that I've tacked on here was the idea of the Npp plot. How many of you prefer the histogram? Npp plot? Couldn't care less? Okay, thank you for being honest. All right, I am lazy. Yeah, that's me. I'm lazy. I like to be the easiest thing possible, so I'm going to go with the Npp. But when I do your as often as possible, just so that the folks who chose one method or the other understand that they both work. You do not need to do them both. If you're doing an NPP, you must label it NPP, a normal probability plot. If you're doing a histogram, you must label it bag weights. Okay? That's as detailed as you need to get on those. All right, the reason why I pushed back the quiz was because of this guy right here. We didn't get to this. It was the only thing we didn't really get to. And that is how the average proportion that we were given, the P, or we could use our worst case scenario, which was the 0.5 for P. That would maximize the sample size. Now, the problem with place where this gets difficult is in order to solve for n, we actually need n. Do you see that? N does not kind of affect this problem in just one place. N affects it here and here. And I could solve for this if I knew that value, but we don't. So when we are finding a sample size for means, we have to start by using Z star first. Okay? It's not horrible. I actually think it's a lot easier than when we were finding sample size for proportions. Because, think about it. Proportions, we had root PQ over n. Now we don't have all of that. We just have S over root n. It solves so much nicer. But we're going to have to start with Z star to approximate this. So what I mean by that is we now have this formula that the margin of error is equal to T star n minus 1 degrees of freedom times S over root n. Again, with this stuff, I don't think it's best to plug the numbers in. I think it's best to solve for your variables first, then plug the numbers in. So if I want to get n by itself, I'm going to times both sides by the square root of n, and I'm going to divide by the margin of error. So now I'm to the point where I have root n is T star n minus 1 degrees of freedom times S over ME. Everybody okay with what I did there? Just doing a little bit of baby algebra. Get the n out of the denominator and then try to work to get it to itself. And what do I need to do to finally say what n is? Square both sides. So we will say that T star with n minus 1 degrees of freedom times S over ME squared will give me my approximation. What we're going to do, because the sample size is needed for T star, we're going to put in a little bit of an approximation first step. We're going to use Z star instead. You're going to use Z star instead. Find n. Use it for the degrees of freedom. then use T star with your degrees of freedom to find n. So those are our steps with this. We need the sample size. I can't find the sample size unless I know what my critical value is. So we approximate it with Z star. That gets me a starting point for degrees of freedom. And then I can use those degrees of freedom to find n. Now technically, you could keep kind of spiraling through this to kind of get it more accurate and more accurate and more accurate. I'm not going to make you do that. You're going to go through it once, and that's good enough. Okay? Ready to try this? I don't think this is nearly as bad as using proportions. So go ahead and read through this problem. Write down what you know from this given information. So what can I pull from this? What's good here? I got a couple numbers. What's 2? 2 is the margin of error. What's 99? Confidence level. What's 4? Standard deviation. So that's standard deviation of the sample. So I just grab those things, and I'm going to use exactly what I said. I'm going to start this thing using Z star instead. So I'm going to set up that my n is equal to Z star. How do I find Z star? I'm going to use inverse norm. And I'm going to do 0.5 plus 0.99 over 2. Find that sucker. So I get 2.57. I'm just going to do 6. My standard deviation was 4. Margin of error was 2. And I'm going to square that. So I'm going to say times 4. Try to get that glare off. Times 4 divided by 2 square. And I get that n is, and what do we do with the sample sizes here? Do we round to the nearest number? Do we round up? Do we round down? What do we do? Round up. So here I have n is 27, because they just said round up. So far, so good? Now we're going to use that guy to now calculate degrees of freedom. So if I'm using that, what is my degrees of freedom? 26. So I'm going to go back to this equation, and I'm going to say n is equal to, and I need the T star with 26 degrees of freedom. How do I find T star? Inverse T. So again, the 0.5 plus 0.99 over 2. Degrees of freedom, we've said is 26. Chicka, chicka, chicka. Think, think, thinks. So I've got 2.779. Still with the same things. Times 4 over 2. And square it. So times 4 over 2, which is kind of, I could have just done over 2. Or times 2. Squared. And what am I going to say n is? What am I going to say for n? Do we round up, round down, go to the nearest integer? Got to go to 31. 31, and we need what? 31 jars. Because that's the context for this problem. So we started with using Z star. Use that to find N. Use that to find the degrees of freedom. Use that to find T star. And then use that to find N. Yes, sir. Or did you want to actually see I didn't know if you wanted the calculation or you wanted the final. That would be a problem. And if you forgot to divide by 2, it probably gave you an error sign. Yeah. So that's going to be your big thing. Because you know that your area has to be between 0 and 1. All right. So you can see here. My goodness, people. Sharing is not caring with germs. Keep them to yourselves. All right. Are we okay with this? It looks a lot more intimidating, in my opinion, when it's written this way than if it's just this idea of Z to N to T to N done. Okay? And that's why I didn't want to give you guys as your quiz, because that one last little concept we hadn't covered. Now we've covered it. Yay! Right. Hypothesis test, confidence intervals, sample size, 1 sample. Okay? Correct. And your marshmallow investigative task is only on 1 sample. So it's only on what we've done. Because people try to do it with 2. Don't do it with 2. We're trying to keep it easier. Okay? Everybody clear on that? Your investigative task that's in your packet, the marshmallows investigative task, is only about Chapter 22, 1 sample. Yes. That is going to be due. Let me see here. I've got it written down in this. Next class. Wait, is it next class or is it class after? Monday. Monday. It's due Monday. No, because you didn't want to type this up. Right, wait, was it Cameron that typed it up? Cameron's a dork. It is not fun to try to find these symbols. I mean, if you want to type it up, okay. But no, you're doing it by hand. So Monday. I mean, if you really wanted to, especially if your handwriting stinks, but your handwriting doesn't stink. I like typing because of spell check. I feel better that way. No, you're bringing it into class. I don't even have it set so you can submit it in to Canvas. All right. Do you get my joke? Do you know who that is? Okay. There's a reason I teach math. A little reason. Alrighty. So what we're moving on to today is what happens when we compare means. Again, not on the quiz. Don't use for the marshmallow investigative task. Okay? Alright. So life is always more interesting when we compare 2 groups, because we don't normally know what's true in the past. We usually have samples that we use to estimate what happened in the past. So I've got to be able to compare a present sample to a past sample, or a sample of women to a sample of men. Okay? Or a sample of double stuffed Oreos to a sample of regular stuffed Oreos. Or if you talk to Mr. Shepherd, who was so proud, he got like the 4 times stuffed Oreos, mega stuffed, and then he had his kids like scrape it off and do it 2 of those. So he was like, times 8 stuffed. So you need to be able to compare these things. So one of the first things that we did for comparing distributions was we talked about, okay, let's look at it. And we did side-by-side box plots. We did side-by-side histograms. Okay. Bar charts, those are categorical data, so that doesn't count here. But the box and whisker plots are really easy to compare side by side because you can see where the median is for both of those. You can see a general idea of spread, and you can see right away whether or not you have outliers. And it's still nice, though. The problem with looking at the visuals is we don't get a clear-cut yes or no type of an answer. It's like I look at those and I'm like, heck yes. Those look like there's a big difference. And this is actually, I think it was the calories for brand name versus generic yogurt. I don't remember, whatever. Okay, it says duration, brand name versus, I have no idea what that is then. So when we compare two means, it really follows very similar steps to comparing two proportions. But remember with proportions we had pooled and not pooled and pain in the neck or regular. We don't have that with means. Means is so much easier. So what we are interested in here is instead of P1 minus P2, now I'm interested in mu1 minus mu2. But generally, all the rest of this stuff is going to stay together. So now the biggest tweak, if you remember from when we were doing proportions from 1 to 2, is we need our standard deviation. And we've even seen this before. We said that if I'm comparing two standard deviations and I want to say A minus B, we don't do math with our standard deviations. We do math with the variances, but this is on inside, and variances only add. So you've actually done this. You just don't remember doing it. And the big idea here is that we take sigma squared over n plus sigma squared over n, and then the square root of all of that. But as we've seen before, we normally don't know what sigma is. We don't know what the true population standard deviation is, so we use our samples. And therefore, we call it a standard error. Now, the thing that changes the most with means is our degrees of freedom are going to change a little bit more. And this right here is a two-sample, either t-interval or a t-test. But we want to make sure that we are denoting the fact that it's a two-sample and not just a one. Okay, so the big thing here, understand the general idea between the idea that variances add, they never subtract. And to go from a variance to a standard deviation, we then take the square root. Hopefully nothing here has blown your minds. You all right? Okay. All right, so our assumptions and conditions. Guess what? They're the same. Except for, what did we do when we went from one proportion to proportion? Independence of groups. That is the only different thing that we're doing here from what we said in the past. So we still have the idea of the independence assumption. And we need to be careful, and I'll be honest with you, the worst part about the two samples is you got to check your conditions for both groups. That means you're going to need to draw your pictures for both groups. That's the most annoying thing. But even with that, it's not too horrible. You need to make sure that you check your assumptions with each group. That means each group should be randomly collected data. If you're doing an experiment, your data has to then be randomly assigned to the two groups. That's what keeps the groups independent. Okay? And if we can't have random, we want that representative. 10%, we don't really go into checking, and if you leave that completely off of your test, okay, I'm not going to hunt you down and hurt you. It's okay. When we talk about means, we only really use the 10% condition if we say that I know for a fact that I'm only making 1,000 of these Louis Vuitton bags. I don't know, I was trying to think of something that might be limited supply. What? I don't even know. Okay. So something that you know has a limited supply, yeah, you want to check the 10% condition. The normal population assumption still is the same thing. And like I said, this to me is the most irritating part. You got to check it for both sets of data. But even with this, I can show you pretty quick and easily because I'm not actually making you calculate all this stuff by hand. It comes from your calculator. Yay. All you have to do is when you're in your stat plot, you switch from list 1 to list 2. So you can still put everything in. You can still get all the graphs that you need. And if you wanted to, you can, no, I would still recommend graphing them separately. Okay? And then we tack on the idea that the two groups have to be independent of each other. See, this is why I like this time of the year. Once we've struggled through proportions, it's like, here comes another one, just like that other one. They just keep repeating itself. It's like nothing's new. You get to start to really get good at that. Okay? Can we see a silver lining? Ish. It's cloudy outside. Tiny silver lining. All right. Your test statistic. Hey, guess what? Before you freak out as to all the stuff that's on the board up here, it is still the same test statistic we've ever had, which is observed minus expected over standard deviation or standard error. Exactly the same. It's just that what we're talking about here is we're talking about a difference in proportions. So we say my observed difference minus my expected difference. And when it comes to means, you can expect a difference. Like if I wanted to talk about average height, I expect there to be a difference in average height for men and women. Right? Most people are like, yes, we all know men and women are equal, but they're not equal in height. Okay? You get it? They're not equal in height. They're not equal in weight either. There's a difference there. And so maybe we believe that the difference used to be 2 inches and maybe now it's changed. Maybe it's closer. Maybe it's less. So you might have a single number from this, or we might say there is no difference between the two groups, in which case, what would that number be? 0. And the most irritating part of this is you're going to have a weird formula for degrees of freedom. And it's funny because it is actually in chapter 23 in your textbook. They give you these like a couple different crazy options. And then you look at the subnotation, it says, don't use this! Nobody ever uses this. This is what your calculator is there for. Your calculator will calculate the degrees of freedom for you. Big breath. Okay? So, just know that your standard error is this guy. Seriously, the T-score formula, I don't even know what it is. Or your degrees of freedom formula for this, I have no idea. It's some really whacked out, crazy, oh my god, my brain hurts formula. All right. So, a 2-sample T interval. Honestly, I loved making these lessons because literally it was just cut and paste old stuff. Assumptions and conditions met. Confidence interval is observed difference plus or minus test statistic, T star. Standard error of the difference, where the standard error is that same thing that's been up on the board a couple of times now. I'm sure if I tried really hard, I could talk faster. It takes some serious effort. And the critical value, your T star, does depend upon your confidence level and the number of degrees of freedom. And I put just a couple like asterisks there. Dude, now I'm like really curious as to what that formula was. I mean, it is ugly. It is like fell off the ugly tree and hit every branch on the way down. Must show. Just to give you guys a little bit of an, oh my gosh! That's the formula for degrees of freedom. Just to show you that it ain't pretty. And even if you see here, it says if you really want to know what it is, look at the footnote and it says, aren't you sorry you looked? So yeah, that's the joyful world that we are living in here. Okay, we're going to use our calculator. Simple as that. All right, so interpretations, your favorite things in the whole wide world. She said sarcastically. Go ahead and read. What you talk about, Wiz? Okay. By the way, just in case you're curious, since we do most of our math with our calculators, we don't need to use the tables that are in the book, and our calculator will deal with the degrees of freedom in its STAPS programming. Folks that don't have that typically look at their 2 sample sizes take the smaller one minus 1, and that's the degrees of freedom. That's the safe side method. Okay, so if you're looking for, I don't know, if there's some reason that you're stuck out in the world and you're wanting to do a t-test and you don't happen to have your calculator, they'll give you your degrees of freedom, but you have the table because, you know, this is the real world, you can take the smaller sample minus 1. Okay? All right. Hot dog, hot diggity dogs. All you need to do is read the ingredients label once on a thing of hot dogs. And then you will only buy kosher from there on. It's like, ew. Okay. A test of the null hypothesis that there's no difference in mean calorie content, one-sided or two-sided? Two-sided. Right? Everybody okay with that? That there is no difference, that's two-sided. This is my p-value. If I had made a one-sided test, what would that p-value have been? Give you a hint, starts with a point. 0.62. How'd you get that? I know, it's like crazy math. Divided it by 2. Because if we're talking about a two-sided test, not equal to, that means these two wings here. If I were to just talk about greater than or less than, I would just be talking about one of those wings, so that's half of the p-value that we calculated. So a p-value for a two-sided test. Two-sided test matching with a 95% confidence interval. What's alpha? Two-sided test, 95% confidence level. What's the matching alpha? I just didn't hear. Shmoomity boobity. We know that we're going to be taking 1 minus 95, or 100 minus 95, right? The question is, to divide by 2 or not? No, because it's a two-sided test. The 2 is in the name. It's not in the formula. So what is alpha? 0.05. So what decision would you come up with this? Based off of that p-value. Would you reject? Would you fail to reject? You failed to reject. So fail to reject in terms of a confidence interval. Would the confidence interval contain 0? I'm just hearing people trying really hard not to be noticed. Yes, it would contain 0. No, it would not contain 0. We have failed to reject. Translate that. We do or we don't have. We don't have enough evidence to say there's a difference. There's no difference. So where's the 0? In or out? In. The 0 would be in our interval. Okay? All right. Read and interpret. Talk to each other. So understanding the fact that in here we have the average for the top load versus the average for the front load. The whole interval is negative. What does that mean? The front is a bigger number than the top. So in terms of the context of this problem, what does that mean? Yeah, front-loading washing machines have a longer cycle time. Each of the different types of washers, by the way, have their own pluses and minuses. People don't just abandon all of the top loaders because the front loaders use less water. Top loaders go quicker. So if you've got a house full of little kids and they're just going crazy through their clothes, you want to get through that if possible. So different people need different things. Okay, so that says to me that the mean cycling time is probably higher for front-loading machines. Just what you said. What does the fact that the confidence interval does not contain 0 indicate? What does that say? There's probably a difference. See how nice and quick that was? 0 is not in the interval. There is a difference. And if you want to talk statistically, we call that a significant difference. Statistically significant. Practically, it's all about you. If we use the interval to test the hypothesis, what would be the corresponding alpha level? What do you think? 0.01? What is your alternative hypothesis going to be? If you're saying does not equal to, that's one or two-sided? Two-sided. So if you're saying not equal to, it's two-sided, and not equal to would have an alpha of what? 0.02. We clearly see there's a difference. So what's another option that you could have said for your alternative? Symbol. Less than 0. And if it was less than 0, what would your alpha have been? 0.01. So it depends upon what you're talking about here. If we're sticking with the idea here that it is just flat out comparing the differences, then the alpha level is going to be 2%, 0.02. Sometimes what people do is they'll say, well, based on this, I'm only going to look at this one-sided test. Okay? So as long as you back up your reasoning, I'm okay with that. All right. So this is not an A, B, or C problem. It's not multiple choice. I want to know why each one of those is either true or false. Obviously, if it's true, you're not going to do much explaining. But if it's false, you got to give me something else. Just take it one at a time. Read A. Would you use that as an interpretation? Would you go with that? Would I mark that correct? Gleb, no? Why not? Okay. Good. That's a very good piece. So for this one, and a little additional thing, really the main focus here is this is saying of all top loaders. Even if we were to have narrowed down the focus to be just the ones that are the good or whatever, or excellent, even with that, you need to make sure that when we're interpreting a confidence interval, when we're going over there, it says based on our sample, we're blank percent confident the true population parameter. What's the population parameter here? It's not just time, it's average time. Because average is the parameter. Time is just the context. All right, if I chose a laundromat's top loader, there's a 98% chance my clothes will be done faster than if I had chosen the front. Yes or no? What do you think? Just generally. Good, bad? Sush, why not? It doesn't sound right. Well, you're correct. It's not right. What was wrong with A? What did A need to have in it? An average. Does B talk about an average? No, B is talking about probability for one specific machine. Do you see what I'm talking about there? That's where the problem is. We are talking about one specific machine here, not about averages. And our confidence interval is not a probability. It's basically how often will these processes generally be right. Doesn't mean that I have a 98% chance of being right. Okay. All right, C. What are they interpreting in C? They are interpreting the confidence level. What gives it away that it's a level and not an interval? Yeah, if I tried more samples. The idea that they're talking about more samples is the fact that they're doing a confidence level here. And if I go over here, I'm not even looking at that. Confidence level says if repeated samples were taken, about percent of the resulting confidence intervals would contain the true population parameter. The only numbers in that are the confidence level, and it's a technical term for it. And 22 to 40, what is that? That's the interval. Your confidence level. Is confidence level generic or specific? Generic. The interval is specific. They're trying to mix the two. You can't do that. Okay, your confidence level is generic to any confidence level you would create, or confidence interval you would create. You're not going to specify what you got. Now, your interval, however, that is specific. Okay. Still same issue. True or false? Read. What do you think for D? Yes, no, maybe so. Why not? Be committing. Be committed. Commit. What are we interpreting? Level. More samples. I'd expect 98% of the resulting confidence intervals to include the true difference in mean cycle time for the two types of washing machines. Yup. True dat. Questions? Okay. What about E? 98% confident that top loaders wash clothes an average of 22 to 40 minutes faster than the front loaders. When you have to do like 10 loads of laundry because you've got a tiny, tiny baby and toddlers and kids playing sports, that time adds up. What do you think? Yes or no? True? True dat. Ow. Ow, that hurt. Ow, hello. We're still working? Okay. Meow. Good. That's true. That's the interpretation of an interval. Specifically, I'm 98% confidence in my... He's saying I'm 98% confident because that's kind of saying this is what I have found. This is what I believe. This is based on what I have done. All right? Okay, what about a hypothesis test? Do we need to stand up and like do a little shimmy, do a little shake, do a little stretch? You guys are falling into sleepy land. I'm sorry, your ears are probably now bleeding from my amazing yodeling abilities.
Actually, wasn't that bad.
You feel, you say that when you look like you're on like NyQuil. I feel great. It's awesome. All right. Now there's one little symbol here that I want to introduce you to. Class, meet delta. Delta, meet class. Triangle. Yes. What does delta stand for? Change. Are you in calculus? Well, good for you for knowing that anyways. Delta means change. Oh, they do that in apes?
We did.
You did? Okay. Okay. So, delta means change. What's another way of thinking about change? The difference. Yeah. You're too cute. Don't teach us tricks. Yes, delta. It's like this just got awkward real quick. Delta is the change. Change is also the difference. So just another way of writing it. So this delta sub 0 is basically saying that one value you have in your null and alternative hypothesis. Okay, I just don't want you to go if you see that written someplace. You've met delta. You've been formally introduced. But you can see here to find my test statistic, just like it's always been. Observed minus expected over the standard error, where the standard error, he ain't changing at all anyways. Okay? And the degrees of freedom, still that, oh my God, dear Lord, make that go away formula. Or the, yay, my calculator automatically did it for me. Or the smallest sample size -1. Whichever one of those things you want to use. I typically go for the, yay, my calculator did it for me. So when we have conditions met, we get to use that t-score to calculate the if the null hypothesis had been true, the probability of seeing a sample as extreme or more than ours. I think she said those words before. Again and again and again. Make it stop. All right. Read. Wally World or Target. I'm trying to fake being awake. What am I asking you to do here? Check. What?
I want to say the assumption.
Assumption, oh. Well, in geometry, in statistics, we kind of have to do our assumptions. Life's not perfect. Yes. When you assume. You pay attention. Yay. Assumption. So, what is my first assumption? Independence. How do I check independence? Randomness. What do we have? Systematic sample. Does systematic involve any randomness? It does. The starting point is random. Okay? So is it going to be the most random thing in the world? No. But it does have an element of randomness built in. So we would say because it's systematic, we hope it's representative. We hope what's representative? Of what? We're doing 2 samples. But the samples refer to 2 things. I'm trying to pull it out. This is me pulling it out of you. What are my groups? Walmart and Target. So what we're talking about here is you need to make sure that you come out and say it. If you don't say it, if you don't do it, if you don't show it, it didn't happen. So those shoppers from Walmart and those from Target should be representative samples of those 2 stores. Do you understand what I'm talking about there? Each store should be relatively representative. What else do I need? 10%, meh. Yeah, so you can see why the 10% gets a little bit difficult to deal with here. What else? NPP, or nearly normal condition. Did I give you data? I didn't give you data, I gave you what? What are these called? Statistics. Hey, welcome to the class. Statistics. These are statistics. Data would have been, here's shopper 1, here's shopper 2, here's shopper 3, 4, 5, 6, 7, on and on and on until you're blue in the face. Okay? I didn't give you data. When I don't give you data, what do you need? Okay, we're just thinking about the conditions. If I don't have the data, because typically someone said NPP. NPP or histogram we would use to justify that. I don't have the data. What do I have? N is the sample size. Do you remember talking about what role sample size had to play in this? A little fella named the central limit theorem. Sample large enough, you could assume sampling distribution will approximate the normal model. Remember doing that? It's bigger. That's a pretty good size sample. So as long as you don't have like Elon Musk going to Target and buying out the entire store, which would be a slight outlier, right? A little bit. Oprah Winfrey coming in, you get a box of donuts and you get a box of donuts. Everybody gets a box of donuts because it's Target or Walmart. They don't sell cars. I was really trying to go there with that. It didn't work. We would say 85 and 80 are both large enough to assume the sampling distribution is going to be normal. I need one more. What else do I need? Say it again, Sam. I know your name's not Sam. Say it again. We need to say the groups are independent. That's from the Maltese Falcon. Say it again, Sam. I was not calling you. All right. So we have to assume the groups are independent. Because let me tell you, if I'm going to Target in the middle of Haymarket, and I'm going to compare that to a Walmart in rural West Virginia, I don't think that those guys should really be compared. Do you understand why? Target and Haymarket, a little hoity-toity compared to a lot of the other Targets. Walmart in rural West Virginia, probably a little bit different clientele, different income levels, different things that you're going to buy from Walmart. I start talking like that, and I'm not going to be able to stop. Okay, so for the most part, we're pretty good. As long as, we don't have the data, as long as there's no like really horrible skew or really crazy outlier, you should be okay with this data. Okay? Wow, you guys are like high level energy today. Read! Children. No fighting over a tiny piece of paper. Are we passing notes in class? It's a receipt. Dollar bills, y'all. Problem. On the board. Yeah. Come on, guys. Folks, please. Kayla, interpret for me. Spotlight. Mm-hmm. Beautiful. There's one little criticism I would say. Because these are negative, what would we claim? Who's more expensive? Because since before what we were talking about is we were doing Walmart minus Target, I'd assume, is that we would generally say that we would expect Target to be more expensive than Walmart or have a higher purchase of amount by between $1.85 and $14.15. When we're talking in context about this, just stating what the interval is sometimes kind of confusing. So instead we say that we think this one is more or this one is less for that. Really, the only time we say the difference is if it might contain 0, because then we're not saying that one is greater than the other. Okay? All right. So I don't think we are going to have... we can get started on this. We'll get started on this, and then we will finish it next class. So is this in your notes? I don't know. Take a look at your note sheet. To beat or not to beat? You've got yours. would be all the way up here. Nope, you don't have this. Okay. So what I want you guys to do is I want you to start by copying down what information you think might be important with this. Start with, let's start painting the picture. What do we have? What are we talking about? That usually involves identify what your parameter of interest is. Since we're talking about 2 samples, identify your groups and write out all of the things you know about your groups. Okay, did you guys get that stuff written down? What I wrote down is I said, starting off with, we're talking about here the resting pulse rate. So mu is my resting pulse rates. Identify my parameter. I'm talking about smokers and non-smokers, and I'm identifying those as groups 1 and 2. You could have used S and NS or N if you'd like. 1 or 2 just to me is a little bit easier to kind of talk about what I've got. I've written down, notice using this notation, X bar 1 is 80, S1 is 5, N1 is 26. X bar 2 is 74, S2 is 6, N2 is 32. Yes. There's no difference in saying X bar or Y bar. You could have even said X bar and Y bar for the 2 different ones, just as long as you keep it straight. Okay? Y'all all right with that? Now that I've got my general data, whether I'm doing a hypothesis test or a confidence interval, what do I need to do next? Assumptions and conditions. Once or twice? Twice. So I need to do assumptions and conditions for both groups. So if I go back to this, what am I starting with, assumptions and conditions wise? Independence. So do we have independence within one group and within another group? Yeah, what? Okay. We were told both were random samples. Random. Random, that spells with an M. What else do I need? So we said independence, which is random samples. Am I going to really worry about the 10% condition here? I mean, I have a feeling that there are more than 260 smokers and 320 non-smokers out there. So I'm not really going to worry about that. You only worry about that when you think it might be close. So what comes next? The nearly normal population assumption. What do we have? Come on, guys. What did I give you? Both sets of data were roughly symmetric and had no outliers. So, what I can say is because of that, with N1 at 26 and N2 at 32, we are going to be large enough to do what? To assume nearly normal. Bless you. We will finish this up next time. Finish your homework up, guys. And investigative task. Thank you, ladies and gentlemen.